Okay, this is week 6 for Program Logic Controls 2, talking about the panel view HMI. And so what we're going to start is we're going to start by taking attendance. So if you're on the D2L, I can see who logs in, and I'll take attendance. People begin their papers back, their labs and their homeworks, kind of staying caught up. If you're running behind on your labs, you just want to keep coming into open lab and try and get caught up as much as you can. This could be a little bit of a shorter session, I hope. We're going to have a couple of long sessions later in the term to make up for this one. Let's start with our Lab 5 review. Now, this was the grinder motor where we originally hooked up, a basic circuit, and I told you that if you just follow the instructions and try and understand what's going on, it usually went pretty well. We had some people, mess up because they were just, reading instructions, not trying to understand what was going on, the difference between left and right, which limits which is left and right. But, it took them a while, but, once we had that basic circuit going, we added, a counter to it, and we'll talk about the state manager required to that. And then we added a run jog situation, which required, possibly some scheduling on there. There's different ways to do it. And then we added the safety relay. And there was a lot of wiring in there. And so a couple of things that a lot of people missed on there in that wiring was that those motor starters were interlocked, okay? And they were they were electrically interlocked. So when they got wired up, the auxiliary contacts from one of the starters needed to go to the coil of the other. So what does that look like? That was basically, this right here, that we had two starters here. I'm gonna put them side by side, and this one had a normally closed, and this one had normally closed. So when we ran, let's say output 1, we ran this through the normally closed, and then we ran it to the coil here, okay? And then this one, output 2, for example, we ran through this normally closed, and then we ran this to this one's coil right here, okay? So if this one was open, even if we turned on that output, it wouldn't run, okay? So this was hardwired with an electrical interlock on those two contactors, okay? Also on here, there was an overload, a heater on here, and it did have overload contacts. And so once again, those overload contacts ran into the input module, and these are normally closed, so that if this goes down, it was going to bring the circuit down. So some people missed wiring in the normally closed overload. So, but that was all the wiring that was involved in that, okay? Also wanted to talk a little bit about the safety relay on this. So we had a couple of things going on with the safety relay. Remember, the safety relay has got, all this crazy stuff going on around here about how to hook it up. But really what we're just trying to do is we're trying to get, 13 and 14 to shut, and or 23 and 24, or 33 and 34, these redundant contacts in here. So when the safety relay was reset, the first one of these was supposed to take voltage through it, and this was DC voltage, and then this was supposed to go to the output module, okay, your output module, and that was where we made the voltage connection onto there. So it doesn't matter, what outputs you have hooked into here, output 1, output 2, output 3, whatever. None of them are going to work unless the DC voltage, the 24 volt DC, gets to the output module. So that was one of the connections. And the other one of these that we were going to do is we were running 0 volts through here. I'm sorry, we were running 24. We were running 24 volts through there also, because that was going to go into an input module, okay, as let's say input 1, so that the PLC could read if this safety relay had been reset or not. So we were using this as an input to bring down the control circuit, okay? So the big one here is, once again, this one here, where the safety relay is supposed to open up the voltage to the output module, okay? And then the secondary, we added an input so that the PLC was monitoring the status of the safety relay. All right, we had a couple of hiccups on that. The basic system looked like this, and mine might look a little bit different. The only thing I did is I got series outputs here, which is, we had this master relay, then we had a light, and cycle relay indicating the light, finish cycle indicating the light. So if you just follow the instructions and kind of put this in here, we've got a memory here. That's kind of like my system bit, or they called it master relay. We've got another memory here, and that's basically, is it cycling left and right, left and right, left and right, or is it just doing a single right? And that is, what this run here did. Was it going to be on a finish cycle and stop, or was it going to be cycling back and forth? And so notice, this was supposed to be mapped, so you had to have a mapped I/O. And so, there's no inputs here. Later on, I'm going to show you some examples, and I do have, the actual inputs in there to maybe make it a little bit clearer, but this was supposed to be mapped. So the basic system circuit, as long as you figured out, what was left and what was right, and which limit switch is left and which limit switch was right, this should have went pretty fast, all right? And also doing the wiring. Now, we need to talk about the state managers a little bit, because we did this with the stamp circuit, and this one had limit switches on it as well, and they were wired normally closed. And so what happens is, this is my cylinder here, and this cylinder goes back and forth. And so right now it's extended, and it's made this limit switch, and then when it retracts, it will make this limit switch, okay? And so the issue is, you want to count cycles. So a full cycle is out and in, that's 1. Out and in, that's 2, okay? And that's what the grinder was. It was all the way over and all the way back, counted as that. And the grinder was neat, so that if you started in the middle, it always moved right, so that it would kind of head home, and then it would start cycling if that's what you wanted to do. All right, what's the issue? The retraction, or the home limit switch, it starts and it's already true, because, or already true or already false, because the item has retracted. And so when you do your counter, you want to have this retract limit switch count, because it's out, in, hit the switch count 1, out, in, hit the switch count 2. But when it starts retracted, your counter automatically goes to 1, even though you haven't did anything, because that's the way that it starts. You can't have that. So in this case, this is just a little an example program. Notice here I've got a start and a system bit, so I've turned on a system bit. Once again, it's always probably a good idea to turn on a little light, system light. And then that system bit is my first state manager. As a matter of fact, I could put that system bit here, and I could put that system bit here, and I could put that system bit here. I could put the system bit on every rung, all right? So that if I didn't enable the system, it wouldn't work. And that's kind of what they were doing here. They had this master relay, and all these rungs had this master relay on it right here. And that was your first state manager, that unless you had started the system bit or the master relay, nothing was going to work. All right, so hopefully you understand that. That's the most basic state manager. But in this case, what we have is right here. The retract limit switch does the counter, okay? So when it goes out, when it comes back and hits this retraction, it does the counter. But notice, if it starts, this is showing true, it would count. But, and that's the way that it starts. But we don't want it to count. So we have to put a state manager in front of it. And what is the state manager? It is the prior process. So if I, a process before this. So I look up here and I find, what is the process that allows the retract limit switch to count? Well, I used the extend limit switch. So in order to count the retract, it must first extend, and then all of a sudden I can count. I can use the retract to count. So when it extends right here, I just give it memory. Next cylinder, I say, hey, the cylinder has extended right here, okay? At which point this is true. So then when it retracts, it will count. Okay, hopefully that makes sense, because even if it starts retracted, it's not going to count, because it has to extend first before the retract counts. And then how do I reset this? Well, here's like a system stop right here. So maybe when I kill my system bit, it stops it. I guess I could have probably put system bit right here. So maybe if my system came down, this memory here, because that's what we did. This extend bit held memory to indicate that it had been extended. Maybe that would bring it down. So that is the state manager for the limit switch and for the grinder motor, and that's critical that you understand how that works. All right. So another thing, state manager we needed for the run jog. So you think about this first ladder logic right here, where you have, a run jog selector. You're either, clicked, you're in run mode, or you clicked, you're in jog mode, run mode, jog mode. So it's either this one or this one. And that was, fundamentally what we wanted to do. The main issue was that, once we went from run into jog back to run, that was supposed to kill the system because we wanted to then start all over again. And that wouldn't work this way because this was either yes, no, or no, yes, yes, no, no, yes, one or the other. And so what we needed was a state manager here to indicate that we went from the running, we went into the jogging, and now we're back to the running again. All right. So what I have here is a system bit again. Now there I did it. I put my system light there. That's probably good. So if somebody hits the system bit, I've got memory. And here's my run mode bit, which is showing up there. So, this won't work because if I just toggle into jog, this opens and my system bit dies and nothing works without the system bit. So that's not going to work like this, okay? So what I did here was, and here I have my cycle start. I could get my motor started. It would hold. All right. So this rung 1 right here, this is just your 131 run jog because I put the run jog selector right here. So if it was open, I wouldn't get any memory. And if it was closed, I would get memory. That's exactly what we did in 131. The selector switch either opened or closed the memory here. All right. And so, what I would have had to add here was limit switches and all that other kind of stuff, but I'm just showing you the basic. But look what I did. So if I go from run to jog, well, this opens, so I'm only going to be able to get a straight shot across here to jog. There's going to be no memory because that's open. But if I go into jog, this is going to close. And I'm going to get this memory right here to say, hey, you've been in jog mode, all right? But instead of just having this run jog selector shoot straight to a bit, shoot straight to the run mode or jog mode, now I have this run jog selector gonna shoot over here to my bit. But when I'm in run mode and then I go to jog mode, it doesn't indicate it. It doesn't bring that true because I have a state manager here, the jog mode. So what I got to do, I got to go into jog because remember it starts in run. We were in run, so this is true, but I'm not getting this run mode bit to kill my ladder logic. Otherwise, I would just kill it right away. It wouldn't do anything. But when I go to jog, I get a state manager that says, hey, I've been in jog mode. So this becomes true. This is false because I'm in jog mode. But what happens when I switch it back over to run mode? Because this is held from being in jog, true. I go back into run mode, true. I get run mode bit, and then bang, kills my system bit. And then everything's done. And my system bit's here, so it would have killed any memory here. I guess I could have put the system bit here to kill this because this is going to be held on as well. I hit the system start. So when I said, all right, let's run it again, I hit system start, it would automatically kill this jog mode again. So that's a way to kind of turn that toggle into like a little bit of a flip-flop. Hopefully, that analysis makes sense there, but this was the easy way to do it. Probably just treat it like the 131 circuit where you just open up the memory, put a state manager here so that when you get jogged, you can be in the jog mode, but it's always going to indicate that it was in jog mode because it's got memory, causing this to be true. Click back to run, true, bit, kills it. All right. and then you have to hit start again to run it. That's what we had going there. Next, here was you know, your jog kills the system, and that's kind of what I was showing you. This is just now, you know, the whole thing where you had your system bits and your hand auto and all this kind of stuff. Is that, you know, if I were to toggle that over to get the, you know, jog kill system, then I kill the master relay, and that's just kind of what I was showing here. I was adapting this a little bit more to the way that, you know, yours would work here, where you would have to have jog mode indicated. Because look, you go hand or auto, you click it. If you go to hand mode, true, 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 flick it back to auto, true, true, jaw, and it kills the system. Bang, master relay down. All right, so I turn that into that. So that's what it would kind of look like in yours. All right. So, you know, I put some scheduling handouts in the packet that you can look at. You know, is this made easier or more difficult with the scheduling of part 3? I mean, a lot of people were getting fancy trying to schedule it. You know, my thing was that, you know, I probably just put the jog mode right here, just put the jog mode right there, and then, you know, if you wanted to turn this on, another way you could do it is just have a parallel rung coming down here, like bypassing everything, and then coming up to the motor starter. And that parallel rung would say something like, you know, the limit switch on the left isn't hit, and I'm trying to hit the jog left button, and it's not in run mode. What, you know, something like that would work as well. Just kind of redundantly using all these contacts. But, you know, this is probably the simplest way. But we had some people, you know, trying to schedule this, and what they were doing is they were using an output more than once, okay? And it's probably a bad idea because you can't figure out, you know, what it is. It does work, you know, but they're like this. They just had this. Here's what I was talking about. They had this hand sub where, you know, hit the forward button. As long as it's, you know, not moving right, as long as it hasn't moved all the way over to the limit switch and the relay was on, bang, it would move left. It would jog. And then when you hit reverse, same thing. As long as it wasn't, you know, dead-headed on the limit switch, it would move right, okay? And then when you went into auto, you know, you would just schedule 2 subs to either go into this sub or you could go into this sub. They just, you know, copied that's part of the logic. See, here's the move left coil. And then down here, you've got your move left coil and your move right coil as well. So you've used the output twice, one in the hand sub, and then this would be the auto sub. And the auto subs just, here's where your memory is. Here's your cycle relay memory. Here's your move right coil memory. So this is the one that's got the memory so that when you hit it, it automatically runs one way or the other, okay? And then their sub look like this. You know, you had your selector switch and you were either calling auto, or here your selector switch and you're calling hand. So you're scheduling this or this. But remember, the outputs in this JSR are retentive, okay? So that just because you unschedule auto, if for some reason in here this had memory and this had memory, when you go back into it, the memory's automatically going to be there, okay? And so, you know, I'll make this a little bit bigger so that you can maybe see. But here what they had was, if the master relay went off, it automatically called subroutine off. And what subroutine off is showing here is move left, move right, off. So what's the problem here? I've now used these outputs 3 times. I've used them in this sub, which is, for some reason, you kill everything, it unconditionally, basically, and it's just going to call this sub automatically and kills everything. You've used those same outputs into hand, and then you've used the same ones into auto, okay? And so, you know, you're going to have some problems here trying to find out what is going on. And so here's what happened with a student. We spent a long time doing that. The master relay right here. So they had the sub where it was in auto, and then they hit their selector and called hand, okay? And it jogged back and forth. It was still, you know, auto still had memory. So when they went back into auto, what it did in their auto somehow, it hit kill master relay, all right? And so maybe they almost had like something in their sub that killed the master relay, not the cycle relay here, okay, in that sub in auto. And so that killed the master relay, which automatically, because they didn't have this, automatically unscheduled both of these subs. And so even though this sub was unscheduled because master relay went back to 0, the thing kept running because this subroutine was retentive. All right, this would have solved that, because if you killed the master relay, this would have automatically called this JSR, which would have turned everything off. Okay, but you got to be tricky about that. You also got to do things like this here. Between you're going back these, you call the jog. If you call the jog, this has got an AFI cycle relay, because you don't want this thing cycling if you're in jog mode. And so sure enough, if you were to cycle back into here, this cycle relay would go down because it turned it off. And when it comes back in here, then it would see. I mean, it gets complicated to try and figure out, okay, I'm going to be jumping back and forth between subroutines. And what tricks do I need to put in this subroutine to kill all the memory in this subroutine? And then what tricks in this subroutine do I need to put in it to kill all the memory in this subroutine, so that when I'm going back and forth, it doesn't do it? And if none of them are scheduled, what tricks in the main do I have to put in to kill all the states, the retentive states, if neither sub was there, okay? And so my advice is, don't use an output more than once, all right? So safety relay, let's go just to reiterate, there's no physical monitoring of the condition of the starters. So we actually, weren't monitoring the condition of the starters. We were just turning them on. Did the PLC really know that the starters, that it was running right or that it was running left? It didn't, because we didn't wire the auxiliary contacts of each starter into an input module. That's what the monitoring of that is. We didn't have enough inputs. We could if we wanted to. Instead, what we did is we wanted to wire one of the inputs of the safety relay, one of the contacts of the safety relay, sorry, this one, into an input, okay? And so then it was monitoring the condition of the safety relay. And if the safety relay goes down, the starters are not going to be on, because that's the way the safety relay works. It's going to bring the voltage down to them. So even though we weren't monitoring those, we wanted to be monitoring the safety relay. How would the safety relay have been added? Once again, we brought down the output source, the voltage. Some people tried to do the output to the motor starters, but we just didn't have enough outputs. So instead of running 0 volts through here like this to your output module, what we're trying to do is they had their output module, and this output 1 ran to the first starter, right? Maybe the forward starter, and output 2 ran to the reversing starter, okay? They tried to put 13 and 14 and then 23 and 24 here. And then you bring them down. It just depends on if you had enough outputs, because we still then needed 30. We would have to then use 33 and 34 for the input module. We would have to use 33 and 34. A third contact is the input here. And this isn't bad. This works. But why not just bring down the voltage, 13 and 14? And then we bring down all of these. We don't need a contact for each output device. We just have one contact for the entire module, all right? So, and then what do we do with that input? Well, I don't know, let me pick some logic here. It's not shown here, but here's a memory circuit on your cycle relay right here. Or let me see, here's your master relay. Maybe that's better. Here's your master relay. Remember, master relay is used here. Everything's got master relay in it. Well, if I basically ran the input that went to 13 and 14 and put a closed contact right here in master relay, well, when I kill a safety relay, master relay goes down. And since whether you were running or jogging, the master relay had to be on. So it kills the memory on the master relay and everything goes down. So hopefully that makes sense. That it's kind of acting like, also this would have had the the overload on it. If the overload of the motor starter went down, open up, kill the master relay. If the safety relay goes down, kill it, open the master relay. If you hit the master stop button, open this up, kill the master relay. All those contacts would come down and then open up, this master relay. And remember, these would be programmed open, wired, normally closed, just like your stop button here. Programmed open, wired normally closed. So that's kind of what we had going on there with the safety relay. Hopefully it makes sense to you. And then all the buttons and stuff that go into the safety relay, the double E stop and the reset and all that. Once again, that has nothing to do, the buttons that get wired out here to make this magic box work, all these buttons, well, they actually have nothing to do with the PLC operation or the motor starter operation or the voltage operations. That's just the operations, these dual channel E-stops here. Those are just the operations of the safety relay, right? So you need the dual channel E-stop and the resets and stuff like that, okay? Hopefully that makes sense. The homework review, I kind of got something like this, and it was, we can take a look at it, but basically what that was doing was talking about low voltage starting, delta Y starting, and that big circuit. The purpose of this is that you can wire a motor. Motors will run on like a Y, or you can wire them as a delta. You can wire them as a low voltage or as a high voltage. That's the way that wiring diagrams work. If I were to come here, maybe I can get an example here and say 9-wire motor wiring diagram. And if we pull one up here, and I go to image, we can find maybe a pretty standard one. I just saw a really good one there. Maybe right here. If I can get this to come up. Okay, so here you go. You can wire these different contacts here, 4, 5, 6, 7, 8, 9 to be run your low volts, or you can switch the wiring here to run the high volts. Okay, and so if you want to try and start a motor, with one of these wiring configurations, you're going to get a less amp draw, and the motor will start running a little bit, and then once it comes up to speed just a little bit, bang, you can kick it over to this wiring, and then it will, since it's already starting to roll and starting to spin a little bit, it won't draw as much amperage when it gets started, okay? And so rather than, typically you would get a motor and say, oh, I want to wire this for low voltage, and you would just wire it like this, wire nut these together, run line 1, 2, and 3, and you would just always just run it that way, or I would just always run it on high voltage. But if you wanted to do this staggered start, you would have to wire 3, 4, 5, and 6, and 7, 8, and 9 through one combination of starters like this, and then you would have to then click the starters so that the connections change to accomplish this, okay? And that was what that handout was talking about Y delta starting, okay? And so basically that's what you were doing here. You had your starter, and then you were going to have a 4, 5, 6, and a 1, 2, 3 starter to kind of flip those wires, one way. When this starter's on, your wires are connected, one way, and then when this other starter comes on, they're connected, another way, and you don't want, those starters to be on, or else you're gonna get a problem, okay? Because you're going to get, a dead short there. So that's kind of what this was talking about, is how to do this startup, whether you start with one wire and it switches over to the other. So that was kind of what the homework was. And hopefully you understand, how that works there. I want to talk just a little bit about some of the starting mechanisms, and we'd get to this in the next PLC class, is you don't really see a lot of, like Y delta starting like that anymore. Maybe, you can see it if you're having a problem when you're trying to start your motor. It's the inrush current is just popping up really fast due to the load and everything like that. And you know what that is? You got time and you got current. And so you get this inrush right here. And maybe it's just popping up too fast right here and you're blowing fuses, right? So that's why you would want to try and start on a lower voltage and then switch it over to a higher voltage, so it would kind of ramp up here and get running, and then you'd hit it again and it would ramp up again and get running there. Okay. But you know, you might not see a lot of that wide delta anymore. Not nowadays. What you see a lot of is soft starters, and the soft starters gradually increases the voltage to the motor, and it allows for a smooth acceleration of power instead of that sudden violent burst that could damage the motor. Okay. And it's solid state. Okay. And you know, that's basically what you would see, you know, a lot today. Is you would hit the start button, and in the starter you would program, you know, like how big of a motor is it, you know, how many amps is it drawing, you know, your time domain and stuff like that. And what it's going to do is it's going to be pretty smart, and it's going to have a little bit of feedback here to sense, how much amps am I drawing, you know, and it'll trip out still. If you draw too much amps, for some reason you can't start the motor, maybe it's locked or something, it's going to trip. But if the motor's starting to spin, then it's going to control the amps to the motor, and it's going to, and it's in the voltage, and it's going to slowly ramp it up, and it'll start. And I mean slowly or gradually. I still mean really fast. I mean like within a second or something like that, probably. But it's pretty smart. You don't have to switch it over. Okay. Another feature of these starters, these solid state starters and the hybrid starters, and a hybrid starter could be used in this technology here, the soft starter, or it could just be, you know, you could have a hybrid starter that would run normally. Okay. And the way the hybrid starter works is like this. When contacts on a typical starter close, there's a lot of arcing that goes across here because they're physical contacts and they close, and you've got a lot of amperage coming through here. You get a little arc, and the contacts get burned and pitted and worn out. Okay. And after a while you might have to replace them or file them down or something like that, or they might weld together. That's why we have all these safety relays, right? And so these contacts moving back and forth, you know, eventually wear out. And so a hybrid starter puts SCRs, or solid state switches, in parallel with these real contacts. And so when you start it, what it does is it uses the solid state contacts because they don't move. There's no arcing or pitting or anything like that. They're just solid state. So these solid state contacts will close, and the motor will start. And once the motor has started, it will, you know, these are still closed. Once the motor started, it will then close these physical real contacts, but there won't be any arcing across them because all the current is running, you know, on this parallel. All right. So then these close, and then it will turn off the solid state. These will all open. Okay. But since we'd already shut these, it will stay open. Okay. And that way, there's no arcing. Same thing when you try to shut it off, it can manage the shut off here so that you just don't open these up and that you get a lot of arcing and you burn your contacts out. All right. The solid state hybrid starters here also can accomplish your forward reversing. They can, you know, do your soft start. You can put your, because it's solid state and it's doing all the current here, you can throw your overload protection all into the starter. Also, you can, these soft starters can have the safety relay, the safety functions of a safety relay incorporated in them as well, so that you could wire your e-stop connections and everything into a hybrid starter. So these soft starter hybrid starters are expensive, but they start putting everything all into one, and so they might be more economical than if you go this way. You got to buy, you know, your low voltage starter, your high voltage starter. You got to wire, you know, all these devices in, or you got to get a PLC to do it. And then you got to put on a safety relay here and safety contactors and dual channel e-stops and everything like that. So, you know, by the time you got to buy all that equipment, it might just be easy to buy, you know, one of these, you know, soft starters that have all this hybrid technology built right into them. All right. Quiz review. That was what we were doing. We were doing a refit of a system, and what we'll do is I can take a look at that next time just to give everybody an idea of what was going on with that quiz. There will be a quiz, after this. So the week 6 topics are managed switch, panel view HMI, and our factory talk view. All right. So remember, we have a managed switch. All right. Now this is supposed to be 168, by the way. We have a managed switch on ours, and the reason we have that you would use a managed switch is because you would want to switch between two networks. So let's say our network is 192.168. I'll make this one. I can even make this one right here, 1-1. So you guys have been setting up all your networks with your partners at a 192.168.1, and somebody's a 1, and your remote IO was 71, and somebody else was a 7, and your PLC was .6. This last number right here was different for all of your networks. This one right here could have been 101, anything, all the way up to 255, right? Well, if for some reason you get all your devices and you do get up to 255 devices on your network, well, that's it. You need another network. And so your new network, you could name 192.168.30.1, or you could name it .2 if you want. I don't know what you want to name it. You're going to name it something with this here. And then once again, you have all the way from 1 up to 255 devices that you can connect to. So now you've added 255 more Ethernet devices. The problem is, and you've learned this, is that when you go into links, if you have your network adapter set to 192.168.1, and then whatever your network adapter is, you don't see a .2 network. You only see the .1 networks, okay? But on your PLC, you might want to pull data from this other network, and it could be a .3 network, a .4, there'd be a lot of networks here. And so what a managed switch does is it allows you to not only look at this network and all these devices, but you can bridge into another network, a .2 network, in all these devices as well, okay? And that's what we would get into that a lot in the next PLC class, because as I had before here, I had a 10 and a 20, and this might be a part of the work cell, a robot, a conveyors and sensors and everything like this, a zone of the work cell. And this one right here, the .20, might be a different zone with its own robots and conveyors and everything like that. But they all want to see each other, and you might have the .1 network being your safety, controlling everything. So that's what a managed switch does. And so we are running through the switch, and I think I might have you guys manage it just for fun. All right. A static switch does get a static IP address. And what we do is we go through and we configure it with a serial connection. We kind of do like the big kids do in the IT when they go through the console port, because those guys that set up switches, they're great. They just type away. It's all type. And so you'll see we're going to go in through the console port, and what that does is that gives us a lot of power, because all we need is a 232 and ours 232 connection into a DB9 port, and then we can just configure that whole switch. And this is similar to what I was talking about, trying to configure devices, because if your device doesn't already have an IP address, you can't see it. And so, we were talking about using boot P and all this stuff to get it all set up. Well, when you have a switch that you're using, you can't even, this is the way to set it up, because it doesn't have any connection ability yet. So we configure it with a serial port, okay? And then we're not going to save the configuration. We're just going to cycle it every time. You can set it to keep the IP address, but all my classes use this switch, and then we configure it each time, and then as soon as we cycle the power off and on, it then loses the IP address. But you'll see when you give it an IP address, it will pop up on links, because it is an Allen Bradley switch, and links sees it as an Allen Bradley device, and boom, it'll be another Allen Bradley device. All right, but we'll run through the managed switch. The panel view that we're going to use is another Ethernet device, and it also needs a static IP address. So you go and you'll set that static IP address, and you'll plug it in, and everybody can see it and share it. Assuming you're all on probably a .1 network, 192.168.1 dot whatever. That's what our PLC is on, and that's what you want to set the panel view to, and then you'll be able to see it. All right. So a bingo board. So when you start, monitor or tracking a process, a lot of times you'll see like a bingo board on a work cell on the HMI. And so what that is you come to the HMI and it might, I don't know, in the simplest form, it's going to look like this. And it's going to have, a lot of indicators like, run. And if the cell's running, this spot might be green. And, if the limit switch is hit, maybe this would be green. And you get some yellows here and some reds, and you'd see, green, 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 yellow, yellow, maybe something red on this. So this bingo board is going to have, all the indicators of what sensors are being hit, what process is running, what outputs run. And you can just kind of look at the bingo board and say, oh, this is all this stuff is running, okay? And, if you go into, some big facilities, sometimes you'll go, and on the far wall, they'll have this massive projector running, okay, and projecting this big screen on the wall, and there'll be like blinking yellows and blinking reds and greens and everything. And if you get like a blinking red or something, whatever the company indicates, this right here, if this starts blinking red, then everybody on the plant floor can see it. And then the tech who's in charge, this blinking red might say something like, robot reset or something, blinking red. Well, then that you got to go over to cell 1 or whatever, and then you got to get to that robot and you got to reset it or something. And then when you reset it, then all of a sudden this will go back to green, and you might want to try and keep this board as green as possible to keep your process running. Okay, so that might be a little bit of your bingo board of your stasis indicator lights. When you're using the PLC, remember you're going to add controls for like starting or stopping it. Just remember that it's not a true e-stop. It can be a stop, but it's not a true e-stop. And it could be a start, okay, that's fine, but just not a true e-stop. You still, in the system, are going to have an e-stop, or you're probably going to have, some type of a safety stop, either with a safety relay or a safety PLC, all right? But the bingo board will still, you can control your process. So we're going to be doing controlling the process, and we're going to be doing indicator lights. Okay, so review the lab. Just come ready to the lab. It's going to be hopefully pretty straightforward. It's a new piece of software. It's called, Factory Talk View. Let me see if I can get it to come up here. View, Factory Talk View. I don't have it on here. I want it to come up. Factory Talk View. I wonder why I don't have this. View ME. Let me just bear with me 1 second. I wanted to just pull it up. I might not have it on this one. Factory Talk. Where's my Talk View ME? I got it all here. Oh, there it is. ME station. When you start typing Factory Talk View, it will come up. But this is what you are going to be running, and it's a new piece of software. And the main thing that you want to do is follow the instructions. I'm just running ME station. Sorry, this is just to simulate it. So I guess that's not what. Maybe I don't have it on here. But when you go to the lab, you want to follow all the instructions, because you have to. One of the things you got to do is you have to use RS links again, because it all runs on RS links, and you want to be sure that you have that set up so that the PLC and the HMI are working together. And remember, the HMI says, where am I getting my information from? I'm getting it from a PLC. So you do have to use, that links to go in there and be sure that you pick your PLC and get it set up, okay? So that might be the hardest part of the lab, is to be sure that you can get that and read all your tags and everything like that, okay? And so hopefully, take a look at the lab and you'll see that it goes well. It says quiz and lab. The quiz is going to be open. Like I said, it was a short lecture. Be sure you review the lab and be sure that you're ready, and hopefully you understood the issues of the state manager and stuff like that. But that's what I have for you.